Good afternoon, and thank you for coming. I'm going to talk about short story about my life at the UAF. My childhood, I was born in 1930, and boyhood was about 1936 till 48, and young adulthood 48 to 58. I was born near Mount Asama, it was a very active volcano, about 10 miles from my place, and erupting all the time. This is a picture of my mother and me, and she had a favorite song. I think the title is something like Drifter song, and the opera song based on Tolstoy's story. And first part is say something like, should I go ahead further or should I go back home? I'm wandering under the aurora. And that's the first time I heard the word aurora. My boys' days, our school was closed. It became a big car factory because that's what during the last war. And we had to, of course, there are no classes, which is good, but we learned how to use big machines and milling machines, and I was in charge of making a part of a stick shift part. University days, 49 to 58, 19 to 28. Meantime, I was, about 2-3 years, I worked at Nagasaki soon after graduation, so that includes my graduate student days. But I was not very much interested in studying, and most of the time I'm mountain climbing. So my father said I graduated from Department of Mountaineering. But in order to skiing, mountain skiing, you need all kinds of tools and need money. So I tried to find a job to get money, and then I finally found the one at the Magnetic Observatory. I didn't know what the Magnetic Observatory even meant. But anyway, in the observatory, there is a machine called magnetometer, and it works this way. Here is a little magnet hanging, a thin string, a mirror attached, and the light beam is sent to the mirror. So when the magnetic field changes, magnet wiggle a little bit, then that amplifies the mirror movement, and then light beam goes to this spot. And then there is a cylinder, the photographic paper wrapped around it. This cylinder rotates once a day, so my job was to change this photographic paper and then photo process once a day. That's part of my job. This is done completely in darkness, of course. So all I could see in the dark room was a small spot. And I was watching it, and it moved in wavy ways or very large changes, small changes, very, very interesting. I was so fascinated by it, so concentrated on the movement. And then I asked the manager of the observatory what causes these changes. He told me aurora in Alaska or Siberia. The reason is that aurora produces a lot of electric current, and electric current produces magnetic field. That's what we observe in Japan, even that for a distance. So somehow I decided to study the aurora. Then I was told that if I want to study the aurora, I have to read a paper by Syun-Ichi Akasofu and Ferraro, written in 1931. And so I found that in library and started reading. It's very, very difficult, and I must confess that I don't fully understand paper even now. But anyway, I thought I better give up and do something else. But once I decided to study the aurora, no choice. So I decided to write to Syun-Ichi Akasofu and had about 10 questions. And I never expected he would respond. He was the top authority in the field. I was just starting graduate student. But unexpectedly, I got a reply from him saying he cannot answer all the questions, so come under him and study together. So that's where I end up in Alaska. It was December 1958, just before the Alaska became the state. So that's the way it started. As a researcher, actually, I was a graduate student from 1958 to 1986. When I write, of course it's a winter time, but this picture was Geophysical Institute then. It's now a mathematics department, and the director was Chris Helby. But I was still, one of the reasons I wanted to come to Alaska was to climb mountain skiing. So I found Chuck Deere, who introduced me during the award ceremony of the Roger Smith award ceremony. He introduced me, and we did a lot of skiing and also mountain climbing. This is the second ascent of Mount Silver Tip. Also, we had raft race. Raft has to be one-made, and I know the machine involved, so oil barrel, that's the requirement. So we had a lot of fun. Then Chapman came in the spring, '59, so I had to work. I started to work with him. Chapman liked walking, so we had to walk together. He told me many, many things about science and even politics sometimes. I changed the subject. That if I look back, there is one continuous, one method I used to take throughout my research life, and let me explain. To explain this, I have to first introduce the term paradigm. The paradigm definition may be a little complicated. Scientific philosophy definition is complicated, but you can think that of a popular theory of model. And that means that here is the jigsaw puzzle, and a group of scientists work together in a way similar to solving popular puzzle. The group as a whole don't think other than Garfield. Also, of course, don't force pieces in places where they don't fit. In scientific terms, for example, divergence B has to be 0. And of course, you should use scissors or clippers. For example, plate tectonics. Everyone knows that. And under this concept, everyone in this field try to understand how the volcano works and how the earthquake occurs. It's all based on plate tectonics. So this is a good paradigm, example of paradigm. Or global warming. Everyone says that caused by CO2, so everybody work on that and don't think of anything else. In the magnetospheric physics, people talk about what they call magnetic reconnection, and you shouldn't think of anything else but magnetic reconnection. So that's a paradigm. Well, another simple way to explain is this. Here is a model, and what we do is that when you're working on this particular paradigm model, and you say it has to improve the model, that's saying she has a big eyes, a prettier mouth, a dimple, and we do this all the time, nothing embarrassed about. This is the way we work. And this is perfectly logical. This is the way we usually work. But the way I work is that sometimes you find some piece that doesn't seem to belong to Garfield. So what do? Sometimes you throw away, it came from another puzzle, or put it under the rug, or something. I suppose if you start to doubt about Garfield, maybe something, it's not Garfield, maybe something else. Then you start to work on this problem, you see more pieces don't seem to fit. Then eventually you have to put all these together, come up with another puzzle. And maybe end up in another puzzle, sleepy puzzle, instead of Garfield puzzle. That's, in science we call it a breakthrough, or a really big one we call scientific revolution. So let me show you some examples I worked on it. Here is the sunspot, here is the sun, here is the spot, and this is magnetic field, solar magnetogram, and you can see that light one, white one is a magnetic field pointing towards you, and black one is away from you. So sunspot usually you can see appear as a pair, positive and negative. We call positive, light one positive, dark one negative. So the idea is that here is the photosphere, and here is the way the paradigm works is that it started in 1961 by Babcock. Still, most people believe in it. There is under the photosphere, there is a magnetic tube magnetotubule force. And sometimes it's come out from the photosphere, and then here is a positive, here is a negative. So sunspot appear as a pair. But I found single spot, not double, the pair of spot. There is no way you can explain this by magnetic tubule force. I asked many big solar physicists, many of them said it's a broken pipe, but that's not the answer. So, so I started wondering, then it takes an hour to explain this, so let me just say that instead of magnetic tubule force, I think eventually I hope to show that it's a hurricane on the sun. Because maybe the earliest day when people saw sunspot, people thought that that's a window, that in the sun somebody lives there, and that's a window. And then came some people that it's hurricanes, but that's gone. 1961 when Babcock said that magnetotubule force, then everything gone. But now I'm perhaps bringing back. You can see this is sunspot, this is the hurricane. Very much like that. Okay, next subject, auroral zone or auroral oval. The Loomis in 1860, he was a Yale University professor. He worked very, very hard, collected all the newspaper from all over the world, and then determined where you can see the aurora most frequently, and then defined what he called auroral zone. It was 1860. When I came to Alaska, I started to watch the aurora from the early evening. Then I found that the aurora always appear on the northern horizon. Then as time progresses, it's come towards you, and then around midnight, it's be signal right overhead, and then in the morning, it tends to go back to the northern horizon. So I had an idea that auroral zone is this kind of belt, circular belt. It's very much deformed like this. So in the evening I can see a little bit, and then as the time progresses, I can see the aurora come closer, and midnight comes to the overhead, and then go back. Something like this. So instead of the aurora is moving, actually we are moving with the Earth. Of course, I couldn't find all the data, so I just thought about this. Then I found a paper by Yasha Feldstein. Indeed, it's very much deformed. Auroral zone is a peak one. So 6 p.m. Fairbanks dark enough in the midwinter, you should be able to see it. You don't. So he shows that exactly what I imagined. So I decided to support him. But as I told you, Loomis published the paper in 1860, and almost 100 years have passed before I came. I mean, once people believe something for 100 years, it's extremely difficult to say that's not right. So I decided to work on this, and help the first thing. So I decided to build chain of all-sky camera to the North Pole. And then what this chain will do, rotate with the Earth once a day. So it's like airport azimuth scanning radar can see the oval once a day. And in fact, I thought I could prove this well, but that wasn't easy to convince the people. So I had to went to the Air Force, and then I said I need a 4-engine jet plane, and then we flew along the aurora and showed that it's indeed an oval. And eventually, of course, satellite took image of the oval, and so that was okay. Then next subject, the auroral substorm. It was University of Alaska professor Fleur and Bramhall worked on the aurora 1930 to 1934. The main library has some of his material and still have them, and then published in 1937. What it says is that aurora in the evening is quiet and active in the midnight, and then become patchy in the morning. So then the Earth rotates underneath once a day, once a night. So you see in the evening this aurora, then midnight you see active one and the patches in the morning. 3 phases. But when I look at some of the all-sky camera, this is from the Canadian station, Saskatoon. You can see quiet aurora, and then become active and became patches. But hour and a half later, aurora became quiet and became patches, the active patches. Then hour and a half later, aurora became quiet and active patches. So just a few, maybe 1 second or even less, I thought that that night the Earth rotated 3 times. That's impossible. So this means that something is not right. So fortunately, during the International Geophysical Year, Chapman and LB worked together and made a big international effort to install all-sky camera. Camera can take a whole sky, picture of whole sky, and more than 50 stations installed, and they decided to take a picture every minute. It's slow or cloudy, it doesn't really matter so long as in the dark hours. So I had an opportunity, the first time in history that I could see the aurora in Siberia, Alaska, Canada together, simultaneously with an accuracy of 1 minute. So this was a tremendous, terrible work. We had to go through the films from all these stations. Then I found that this is the way I worked. I had the 3 projectors, and Siberia, Alaska, Canada, and simultaneously run. Then this is what I found. The Earth is rotating regardless of aurora. The aurora simply become active and became quiet and then active again. This may, during a quiet day, maybe only once, but active day twice or 3 times. And more details on single activity, it looks like this. Then that's what I called auroral substone. But it wasn't easy to convince the people. So I went to NASA, give me a 4-engine plane that I could use to prove myself. But if you fly from the east coast to Alaska, towards Alaska, it takes about 6 to 7 hours. And the speed of a jet plane and the Earth's rotation is about the same in 65 degrees in latitude. So if you leave East Coast around midnight, your 6 hours stay in the midnight place. So that's the way it worked. I think we spent maybe as much as 600 hours on the plane. Of course, these days, if you ask, I need a plane, they think of like crazy. But those days, NASA was happy to work with us. Then Air Force called me one day, come to Boston, the Air Force Research Center. They found something very strange in Siberia. The Air Force had a spy satellite which looked at the Siberia all the time, the weather, look at the weather so that they can bomb in case of war. And then they found strange, mysterious light in Siberia. So they were very much surprised that Russians are developing new arms, something that we don't know. So I was asked, and then I went, and they, with a white glove, very carefully brought this image, because this is top secret. And then they asked me if I have citizenship. No, I was not to change my citizenship. Then they said, I can't see it. Okay, I came all the way to Boston. What do you do? So they showed me that they made a pencil sketch. Do you think it's aurora or what? So I said, very likely to be the aurora. But unless you show me the image, I can't tell you. But in a month or so, they found that's the aurora. So fine. Then I asked them to release all the images because it's no use. The past data, no use. Then interesting thing that this was one of the images, and then this very much looked like mine study. So that's the way people become a little more confident what I did. This is my first graduate in Maine. Then eventually it was 1982. So my paper was published in 1964. So how many years? Anyway, it took a long time the people convinced them. This picture very much like what I showed. So this image was done by Lou Frank at the University of Iowa. So I went there when they started to receive the data, and I congratulated him for the great data he got, and he congratulated me that I was right. But Lou was very good. Whenever he gave a talk later on, he showed my picture first, and then his. I cannot forget that. So I eventually studied the aurora. We have a solar wind, the solar corona blow out from the sun, hits the magnetosphere and produces aurora. While how can the magnetosphere produce such a spectacular display? That has become the subject of study. And basically, many people think of something quite difficult. I don't necessarily understand what they call magnetic reconnection. But Hannes Alfven, he says that don't think of that way, more about just the electrical circuit. So here is the electrical circuit. This is the way 99% of people are working on. But he was telling me in 1967, I met him for the first time. He said, don't work on it. Think of this way. After all, aurora is an electrical discharge phenomenon, like a neon sign. Global warming. The reason I studied this was that I became the director of the International Arctic Research Center. It's quite a different subject from the aurora. But because I was the director, so I thought I better do something. So, global warming. Everyone thought, practically everyone thought that global warming is caused by CO2. But CO2 started to increase rapidly only after 1946, soon after the last war. But I found I was looking at some records of the glacier retreat, and people say that showing this kind of picture 41 and 204, you can see the same scenery, but the glacier is completely gone. So they say that this is due to global warming. But when I look at this similar glacier, actually what's happened was the terminus of this glacier was here, 1779, 1800. Then gradually started to recede. It's a long time before 1946. So I thought something wrong here. And then I look at this is the Himalayan glacier. This was advertised by IPCC. This is a really good indication that the CO2 is causing retreat of glacier. But as you can see, it began even before 1800. So continuously receding. So something got to be wrong. This is a record that everybody has. This is the only good record with thermometer. Then I found that this is the most trusted reading record. Around year 1000, it was warm, about the same temperature as present. It's called medieval warming period. Then temperature started to decrease. By 1200, it went down to about 1 degree, and up and down. But 1800, it started to recover. This period is called Little Ice Age, and in London you can find a lot of pictures, paintings that even River Thames was frozen in midwinter, and people had markets and people enjoying skating, so on and so forth. That was about this period, a little ice age. And then I found that this recovery from 1800 to 2000, the slope is about 0.5 degrees per 100 years. This slope is exactly 0.5 degrees per 100 years. So it's the same slope. So I want to say that global warming actually started, it's actually recovery from little ice age. Of course, the climate change depends on both natural changes and man-made changes. But if we want to know from the record how much is due to man-made changes, you have to subtract natural changes. Only then you will know how much CO2 has contributed. So this is my view. This is little ice age. This is the straight line is 0.5 degree per 100 years. On the top of that, there is sinusoidal changes, about 6-year cycle. And what IPCC said was that this portion from 75 to 2000 is CO2. So that's why they extended, told the computer this is CO2, so extended something, prediction, say it's about 10 degrees higher than now, year 2100. But my guess is that it's not, because this period combines the recovery and the sinusoidal changes pretty much. So my prediction is that it's simply straight line will be 0.5 degrees, and then depending on the phase of the sinusoidal changes, they go up and down, not 2 degrees or 5 or 6 degrees. This is what NOAA and NASA indicate, as they showed very recently. And what's happening now is temperature after 2000 is flat or even decreasing. And they claim every year, let's say, highest temperature since 1000 years. But they forgot to tell that it's flat at least. So if you go back, that's what I predicted. So I'm the only one in the whole world that predicted that temperature would not increase, at least about 30 years. So just to summarize, I had all kinds of things. I started out with something odd in the paradigm and start to work on it. Another thing, because I'm talking about global warming, big ice age, this is the upper one is a standard figure. Everybody says that there were 4 ice ages, and then this 0 is the baseline, is 1950 temperature, average temperature. They took that to be baseline. But there is really no reason you take this baseline, can be 2000 or 1930. Why do you choose that? There is no reason to. So I decided to choose baseline very bottom. The lowest temperature during the 400,000 years. Then it looks like this. So this is actually heat input. Whatever happened, so you have to change a little bit because of little ice age. Summary, what I want to say is that truth, in quotation, is nothing but what contemporary scientists agree on. Another thing you might be interested in, the people argue all the time with something. How often I see that, suppose we have a pencil, and then one end is round and soft, one end is sharp and hard. They argue. But eventually somebody finds that it's a part of the pencil. That kind of argument goes on. All right. Sometimes people argue, here is the animal that you don't know what it is. Or you say 2 eyes, 1 mouth, 2 ears, or 4 legs. A dog, once group say it's dog, one says cat. So you can make a contribution if you can find something that decide which one. If say something, then either dog or cats say different way. So you have to find something that distinguishes them. That would be a big contribution. Also, the natural phenomena is very complicated. Like a auroral substone, each substones look quite different. I used to say no two substones are alike. But so what do you do? If you try, some people they really got confused, can't make any progress. So the way I do is each one of them looks different, but there's, for example, some element, O is everywhere. Every substone has that. And L, same way, the B, same way. So those are perhaps basic. And then other stuff can be attached. So this is one way to study a very complicated, repeating natural phenomena. Miscellaneous items. One of my students wanted to study, I told him to study ray structure. And then he came to me, he said he needs a big computer. Of course, University of Alaska didn't have it. So I could say, hey, find something else. Instead, I thought I better find the money. So he's Walter Roberts. He's the founder of National Center for Atmospheric Research in Boulder, Colorado. And about a month went by, and I asked him to find the money. Then about 1 month later, I got an envelope. Usually I don't open envelope, I throw away. But this one somehow I decided to open. There was a 500,000 check, nothing in it other than just a check. So this is where I got the money for the computer. And this computer, the first one at the UAF. Before that, at the age, UAF had a very small computer. So my graduate student worked on it, and this is the ray structure actually taken by television, and this is his simulation result. Just one thing, what the scientists want to find is another life in another another planet. And these days you see extra solar system, the star. Now they can even image to planets. So how do you find life? One possibility I propose is our aurora, Earth's aurora, is greenish. And the reason is we have plants. So if you could find aurora over there and find the oxygen emission, then at least there are plants there. Perhaps maybe dinosaur too, but at least some life you can find if you could detect the life. In fact, I was in Caltech a couple of months ago. Caltech really geared up to find life on another planet. So, okay, now change the subject. Geophysical Institute. I was a director from 86 to 99. First one, before I forget, this antenna. This is very important. The GIS stuff are very innovative. And the WikiWix and Gantawera came up with an idea to receive signal from satellite, and the special type of satellite, and got an antenna. The only thing I did was NASA was in charge. As far as NASA was concerned, GIS was nothing but concrete block to put antenna up. So I went to NASA, the administrators, and say, unless you fund research money, I will let you put antenna up. Okay, there was an interesting thing at the GI. Whenever St. Augustine erupted, the director changes. So that's what happened, apparently. That's what our volcanologists said. There are three directors, Keith Maser, one rotary, and Keith Maser was a very, very important person for the GI because he was the one that established atmospheric sciences, seismology, volcanology, everything. Before that time, all we had was aurora radiophysicists mostly. And in fact, when I came, that was the case. So he was the one who made GI as a modern Geophysical Institute. Okay, this is, someone left this picture on my desk. So they thought that I'm trying to hurt the cats. And I could even identify some of them. But actually, my GIA organization chart was like this. Student was the most important, then PI, and the director, and so on, chancellor, and so on. But the GI staff thought that that's not the case. Chancellor is up there, and the director is down there, and the PI is at the bottom, so on and so forth. This is Helga Wilm. She has helped me as a super secretary for 20 years, 13 years at the GI, 7 years at IAC. And someone left this one on my desk, don't know mine. And you can see helpers there, the faculty and the staff. That's why staff's view of the GI. We had a really good administrative staff. I started the GI Thanksgiving, rather than still going on. I like the machine shop. I don't know why, perhaps because I worked on a big machine like that. And then Larry Kozeki wanted to have a computerized milling machine. And it costed at least 250,000. Nowadays, I'm sure $500,000. And somehow I found money somewhere, bought two of them. I had some disagreement with Chancellor from time to time. She was, because understand she was trying to save money, and so she wanted to centralize as much as possible. So tried to take business office, HR office, and I say absolutely no. I was almost fired, but survived. There are two, I remember two interesting findings. One is Sprite Jim Westcott, and then it did some very interesting work on the understructure of the Pacific plate coming under Alaska. Then soon after I became director, the Mount Redoubt erupted. And this was the night before the eruption. We were wondering what to do because volcanologists said eruption is imminent. And then what happened, of course, then that evening around midnight, I was the director of the responsibility to call FAA Anchorage municipality, and I did that. The next morning we heard that the Redoubt erupted. We're happy about it. Then we learned that KLM airplane got into the volcanic ash cloud and almost crashed. This is exactly seen that from flight recorder you can tell what of Alaska range they're looking at. Of course, if they could see it, it's in darkness. So I tried to set up Alaska Volcano Observatory, but I went to FAA, give me a seismometer. They say, seismometer is for the earthquake. Why is FAA in charge of how to give money for seismometer? So they say go to the USGS. But the USGS, they take care of earthquake and all kinds of things. They say, why do they have to pay for aviation? And NOAA, they didn't care. So volcanic ash cloud was sitting among the three agents of the department. No one is in charge that time. So we decided we can do this at the GI because we have volcanologists, atmospheric scientists, the satellite data. This is an example that Hiroshi Tanaka worked on it, came up with a simulation. This is Kamchatka volcano erupted, and this is what he simulated. And this northernmost track is the one plane fly usually from Seattle to Narita. So somehow we got information that Vice President Goa gave us hammer. So we wonder what he meant. What he meant was we broke the walls over 3 departments. Poker flat. Soon after I became the director, the OSHA, Office of Safety something, Health something, came to my office person and then said, close the poker flat. Dangerous. We cannot close it because it's nationally used. This is the only rocket range in the whole U.S. soil. So we have a national responsibility. So what I said was, I agree with you. If I were you, I would close it. At least to say something. He was very happy because I agreed with him. I knew I worked there, and wires hanging here and there, transformers tilting in permafrost, also falling down and so on. So I told him, give me a little time. And I estimated the cost about 20 million. There is no way you can get 20 million any place. So finally I went to Senator Stevens. And I had to convince him that we have a rocket range. And he decided to help me. And he gave me 20 million. But as soon as they heard about Air Force, everybody tried to grab a piece of it. So I had to protect some money. Spent lots of money protecting. But the Air Force took 6 million from it. But so I just asked Senator to give me another 6 million. Well, so now rocket range, launcher is inside, and you take it out, hangar before launching. This was what I wanted to set up Aurora Observatory. This was designed by a group of company people that are designing a lunar base. So this is what I ended up. This is good enough. So it's science for Alaskan. Cassie Berry and Judy Triplehorn, and we worked on it, and it's still going on very well. Then, 1999, I moved to IAC. This was the initial design of IAC. We end up with just this because the budget cut. But I had to go to Japan so many times. I negotiated with the Nippon Cargo Airlines to give me a seat. So I don't know how many times I flew. It takes only 6 hours instead of going back around Seattle. So I learned a great deal about 747. And that's why IAC was built. Again, Senator Stevens was very helpful. He had to write many letters to the Prime Minister of Japan, so on and so forth. So IAC, we had a very big project in the Arctic Ocean. So that's why I decided to step down, and Larry Hinsman took over. Thank you.